Hi everyone, welcome to S Mathematics. Today in this video we are going to see subgroups part 1, that is definition and properties of subgroups. Now what is a subgroup? Before going to the definition of subgroup, we can say that subgroup is nothing but subset plus group. You can take subset plus group, you can write. Okay. Now subgroup, the name itself indicates it is the subset of a group. Once we will recall the definition of a group. What is a group? Group is nothing but a non-empty set equipped with a binary operator or otherwise an algebraic structure which satisfies associative property, existence of identity, existence of inverse for each element, then you will say that it is a group. If the abelian property also satisfies or commutative property satisfies, then you will say that it is an abelian group or commutative group. Now we will see the subgroup. What is a subgroup? What I said, subgroup is nothing but subset plus group you can take. Now before going to the definition of subgroup, we will see some of the properties of subsets of a group. Subsets of a group. Now suppose G is a group. G is a group. Either it is with respect to plus or with respect to dot or with respect to any other operator denoted by circle or denoted by star, like that. Like this G may be any group. Now any non-empty subset of this group is called complex of group. What is complex? Complex is nothing but any non-empty subset of a group is said to be complex. Now this is the subset. Now the set of even integers, if you take, what is the set of even integers? The set of even integers is etc. -4, -2, 0, 2, 4, etc. This will be the set of even integers. The set of even integers is a complex of the group Z plus. That means it is the subset of Z plus. Okay. Now after that, if you take the set 1 minus 1 is a complex of multiplicative group G. Set 1 minus 1 is a complex. Here 1 minus 1 will also become a group, but the complex need not be a group, is it? Next, multiplication of two complexes. Suppose if you are having G dot is a group and M is a non-empty subset of G, M is non-empty subset of G and N is also non-empty subset of G, then how you define the product of two complexes Mn. This is M and N are two complexes of a group G. Then Mn is equal to the set of all Mn where M belongs to capital M and N belongs to capital N. It is called product of the complexes Mn of G. Is it clear? You have to take two subsets and you have to multiply one element from one subset, another from another subset. The product of two elements, if you take, such products if you take together as a set, that set is said to be the product of two complexes. This is the product of complexes. Next, now see the inverse of the multiplication of complexes of a group G is associative. Now that is, if Mn are three complexes in a group Mn in a group, then Mn of R is equal to M of N of R. See here how it is. Suppose G dot is a group you have taken. M, N, R. These are the three subsets of G dot. Is it or not? These are the three subsets of G dot. Now what you are going to prove is Mn of R is equal to M of NR. That is, the product of complexes of a group G satisfies associative property. Now see here, how you define the product of two complexes. Suppose Mn is the product of two complexes. Mn is the set of all Mn where M belongs to capital M, N belongs to capital N. Now you have consider X belongs to MnR. It will be if and only if X should be of the form Mn into R, where Mn is the element of Mn and R is the small r is the element of capital R. Here M belongs to M and N belongs to N according to the definition. Now M, N, R, these are the three elements. M is belonging to capital M, small n is belonging to capital N, small r is belonging to capital R. But all these three are the elements of G because M, N, R are the subsets of G. Therefore, you can say that X is equal to M, N, R because G is a group, associativity satisfies in G. Mn of R can be written as M of Nr. This is nothing but M of Nr. Therefore, the multiplication of complexes satisfies the associative property. Okay, now see the next one, that is inverse of a complex. Now see what is M? M is nothing but a non-empty subset of G. Non-empty and subset of G. M is non-empty subset of G. Now, M is, all the elements of M are the elements of G because it is subset of G, is it? But what is G? G is a group. Every element of G should possess an inverse in G. So, if you take the elements of M, those elements will have their inverses in G. Now, if M is equal to the set of all M, then M inverse will be the inverses of all the elements of M. That is, you will write like this. Let M be any complex of G, then M inverse is equal to M inverse belongs to G, M belongs to M. Is it clear? Now, if you take M belongs to M, then capital M inverse is nothing but the set of all M inverse. Where is M inverse? This is in G. Is it? Where M belongs to capital M. That only I have written there. Then it is said to be inverse of the complex. Now is it okay? Next, the product of the inverse of the product of the complexes. See here. That is the inverse of the product of the complexes. If M and N are any two complexes, Mn whole inverse is equal to N inverse M inverse. It is very easy to observe. Now how you have taken Mn inverse? Suppose X belongs to Mn inverse. X will be equal to M into N whole inverse, where M belongs to capital M, N belongs to capital N. Because according to the definition of the product of the complexes, you have written like that. Therefore, X is equal to Mn whole inverse. What are M and N? They are the elements of G. Being the elements of the complexes of G, they will be the elements of G. In G, A and B are two elements. The property says that AB whole inverse is equal to B inverse into A inverse. So, X is equal to Mn whole inverse. Because M and N are belonging to capital N, capital N, they will belong to G because M and N are complexes of G. Therefore, X is equal to N inverse into M inverse. That means you can say that X belongs to capital N inverse M inverse. Where you have taken X belongs to in Mn in whole inverse. Therefore, you can say that Mn whole inverse is equal to N inverse M inverse. That is the product of the inverse of the product of two complexes is equal to product of inverses in the reverse order. That is N inverse M inverse. Okay. Now see the next one. Next one is, now we are going to define the subgroup. Before going to define the subgroup, what you have learned? You have learned this complex. What is a complex? Complex is nothing but non-empty subset of a group. Any non-empty subset of a group is called complex. Now you have seen the product of the complexes, inverse of the complex, and inverse of the product of the complexes also you have seen. Okay, now we are going to define the subgroup. Before going to definition, we will see one example. Now see here, you have taken Z6, 0, 1, 2, 3, 4, 5, addition modulo 6 you have taken. Why I have taken addition modulo 6 is in order to make you understand the modulo concept also better way. Now take S is equal to 0 to 4 from this 0 to 4. T is equal to 0, 3. Okay, you have taken two subsets of Z6. They are, one is S and one is T. Now the composition table of S we will put composition table. What is the operator here? Addition modulo 6. Now see here, write 0 to 4 here, plus 6 you have to, addition modulo 6 you have to write. 0 addition modulo 6 is 0. 0 addition modulo 2 is 6, 2 is 2. 0 addition modulo 6, 4 is 4. Because 0, 2, 4 all are less than 6, they will be the numerators will be the addition. Here can I recall once A addition modulo MB, the definition of A addition modulo MB is nothing but it is the remainder obtained when A plus B is divided by M. A addition modulo MB value is the remainder obtained when A plus B is divided by M. Now is it clear? Now if the numerator is less than the denominator, then the numerator itself will be the value. Okay, like that you have taken. 2 addition modulo 6, 0 is 2. 2 plus 4, 2, 4. 4 by 6. 4 is less than 6, so you will get 4. 2 plus 4, 6. 6 by 6. The value quotient will be 1, but the remainder is 0. You have to take 0 here. Again 4 addition modulo 6, 0 is 4. 4 addition modulo 2, 6, 2 is 6. 6 by 6. The remainder will be 0 you got. Again 4 plus 4, 8. 8 by 6. The remainder will be 2. 1 times it will cancel. The remainder is 2. Now see the table. If you observe the body of the table, this is called as the body of the table. If you observe the body of the table, all the entries belongs to the set S. This is the composition table of S. Is it? All the entries belong to the S. And next 0, 0, 0. Every element and every row is containing 0 additive identity. Therefore, there exists unique additive identity. Next, see, 0 is the inverse of 0 and 2 is the inverse of 4 and 4 is the inverse of 2. So, every element is having inverse. Next, after that, draw the principal diagonal. This is the principal diagonal. After drawing the principal diagonal, if you observe, here it is 2, 4, 2, 4, 0, 0. So, the entries are placed in symmetric order. Therefore, abelian property satisfies. Therefore, S is an abelian group. Okay? S is an abelian group. Now, see, T also, the composition table for T. This is the composition table for T. 0, 3. 0 addition modulo 6, 0 is 0. 3 is 3. 3, 0. 3 is 3 plus 3, 6 by 6, remainder is 0. So, this is the composition table. Now, this is the body of the table. This is the body of the table. There all the entries are in S, 0, 3. Now, identity exists in each row and each column. Next, 0, the inverse of 0 is 0, the inverse of 3 is 3. Okay, now you got it. This is an abelian group. If you see, this is the principal diagonal, this is 3, this is 3. This is an abelian group. Okay. Now, if you observe S and T are groups with respect to addition modulo 6. Now, what is the main group you have taken? The main group you have taken is 0, 1, 2, 3, 4, 5. This is also an abelian group with respect to addition modulo 6. Already we verified in group theory, groups part 1. And part 1 or part 3 in problems. We have seen there. It is an abelian group. You have taken a subset S and T. These two are the subsets of Z6. These two are becoming groups with the same operator. With the same operator. Being the complexes of a group, they are becoming themselves as a group. Therefore, we can say that S is a subgroup of Z6, T is a subgroup of Z6. Now, what is a subgroup? I said subgroup is nothing but subgroup. Is nothing but subset plus group, you can say. Plus group. That is, any subset of a group which is become a group with respect to the operation of the original group, then that subset is said to be a subgroup. Now is it clear? That's why I said subgroup is nothing but subset plus group. Okay. Now see here. 0, 2, 4 is the subset of Z6. It is becoming a group with respect to addition modulo 6, which is the original operator with respect to what the main set is becoming a group. Is it? Therefore, subgroup means it is a subset. It is a subset which is becoming itself as a group with respect to the operator of the main group. Okay. Now, see the next page here. Now, if you take 0, 2, 3, 4, 0, 2, 3, 4, another set. So, here the composition table for this is 0, 2, 3, 4, 0, 2, 3, 4, 2 plus 2 by 6, 4, 2 plus 3 by 5, 2 plus 3, 5 by 6 is 5, 2 plus 4, 6 by 4, 6, 0. Similarly, you will complete this table. If you observe the entries here, see, if you observe the entries here, you are able to find out 5 here, 5 here. These two are not belonging to the set here. See, A is this set. Therefore, closure property is not satisfying. When will you say that from the table closure property satisfies? If all the entries of the body belongs to the set. Here this 5 and 5 is not belonging to the set. Therefore, the closure property itself is not satisfied. But A is the subset of Z6. Is it or not? 0, 1, 2, 3, 4. A is the 0, 2, 3, 4. It is the subset of Z6. But with respect to modulo 6, it is not becoming a group. Therefore, A will be a complex, but it is not a group with respect to the operator of Z. Is it? Therefore, A will be a complex. That means it is a non-empty subset. If it becomes a group like S and T, then it will be a subgroup. Is it clear the difference between complex and a subgroup? Okay. Now, see the formal definition of subgroup. In order to make you understand the concept clearly, I have given the example. Okay. Now, subgroup. Take it. Let G dot be a group. Let H be a non-empty subset of G such that H dot is a group. The dot, this dot and this dot should be the same. Then H is called a subgroup and it is denoted by like this. H is subgroup of G, like this. Z dot is a subgroup of Q dot, example. Okay. Now see the next. Every subgroup of a group is a complex. Previously we have seen. But every complex of a group is not always a subgroup. See here. See, this is the complex 0, 3, the set 0, 3, yes. It is becoming a group, subgroup. Subgroup will be a complex, but complex need not be a subgroup. See here, it is 0, 2, 3, 4 is the subset of this one 0, 2, 3, 4. But it is not becoming a group 0, 2, 3, 4. It is not becoming a group, closure property is not satisfied. So, what can you say? Every subgroup will be a complex, Every complex need not be a subgroup. Is it clear? That is the thing here. Every group having at least 2 elements has at least 2 subgroups. If you are having any group which is having 2 elements, it will have 2 subgroups. One is the identity element, that is, suppose if you take E, G is having 2 elements, suppose E and A. Now, if you consider the singleton element set E, it will be a group. It is one of the subgroup, and the group itself is a subgroup to this. So, any group which is having at least 2 elements will have at least 2 subgroups. That is, G, E, G are the subgroups of G. These subgroups are called trivial subgroups. These 2 are called trivial subgroups. Other than these subgroups, if there exists any subgroup, that subgroup is called proper subgroup. These 2 are also said to be improper subgroups. There are proper subgroups and improper subgroups. Okay. Now, see here. These are the properties of subgroups after learning. What are these things is, the identity of a subgroup H of a group G is same as the identity of G. See here. What you are saying, G is a group. Is it? G is a group. H is also a group. H is also a group with respect to the same operator, that of G. G is a group with respect to dot, then H is also a group with respect to the same dot. So, because H is a group, there exists identity belongs to H. Now, if G is a group, this E belongs to H, H being the subset of G, E belongs to G. That E, which is the identity of H belonging to G, will be the identity of G. That you are going to prove. Is it clear? The identity of the group and the subgroup are same. That you are going to say. Now see here. Given that H is a subgroup of G, let E be the identity of G and E dash be the identity of H. Now what you are going to say? If you say E is equal to E dash, your problem is over. Now we will prove that E is equal to E dash. Let A belongs to H. E dash is the identity in H. Therefore, E dash A is equal to A. Because A belongs to H, H is the subgroup of G. Therefore, A belongs to G. Since A belongs to G, E is the identity of G. AE is equal to A. Let it be 2. Now, from 1 and 2, you can write E dash A is equal to EA. But what is E dash EA? They are the elements of G. In G, cancellation loss holds. G is a group. Therefore, E is equal to E dash. That means the identity elements of the subgroup and the group are the same. Now, is it clear? This is the first property. Now, see the second property. The inverse of any element of subgroup H of a group G is same as the inverse of that element regarded as an element of group G. Now see here. What is H? H is subset of G. Okay. Suppose if you take A belongs to H, implies A belongs to G. Is it? Now A belongs to H, H is a group. Therefore, there exists A inverse belongs to H. This A inverse belongs to H implies A inverse belongs to G. This implies. Okay. Now A inverse belongs to G. This A inverse will be the inverse of this A. That we want to say. That is, the inverse of the element of a subgroup is the same as the inverse in the group itself. Okay. Now see here. Let B and C. The H is a subgroup of G. Let B the inverse of A in H, C be the inverse of A in G. What is the first theorem we said? Identity element is same in both that is in subgroup and group. Therefore, E be the identity in G and B is the inverse of A in H implies BA is equal to E. Similarly, C is the inverse of A in G. CA is equal to E because the identity of G and H are same. Therefore, from these two, BA is equal to CA. But what are B, A, C, A, B, C? They are the elements of G. Therefore, cancellation law holds. You will get B is equal to C. What is B? B is the inverse of A in H and C is the inverse of A in G. Both are becoming equal. Therefore, any element which possessing an inverse in H, that inverse will be the inverse of the same element in G also. Okay, the inverse of the element in subgroup and group will be the same. Now see the next one. Let H be any group of G, any subgroup of G, then H inverse is equal to H. How you define the complex of inverse? Then the inverse of the complex, if M is any non-empty subset of G, then M is said to be the complex of G. M is equal to the set of all M belongs to G. Now how you defined M inverse? M inverse is nothing but the set of all M inverse where M belongs to M. Okay, now this is M inverse. Now what you are going to say? H being a subgroup, it is a complex. So H inverse means, H inverse is the definition, the set of all H inverse where H belongs to H. This is the H inverse. Okay. Now what you have to prove? H inverse is equal to H. That is, if any complex is becoming a subgroup, the inverse of that subgroup and subgroup are both are the same. See here. Now we prove that H inverse is equal to H. Let X belongs to H inverse. X is equal to H inverse for H belongs to H. Therefore, H belongs to H. H is a subgroup of G. H inverse belongs to H. Therefore, X belongs to H. Where you have taken X in H inverse, you are arrived X belongs to H. Therefore, H inverse is the subset of H. Okay. Similarly, take H belongs to H. H is a subgroup of G. The inverse in H and G both are same. Therefore, H inverse belongs to H. H is a subgroup. Inverse of that element belongs to H inverse. So, H inverse whole inverse belongs to H inverse. Therefore, H belongs to H inverse. H is the subgroup of H inverse. Therefore, H inverse is equal to H from 1 and 2. Now, is it clear? From 1 and 2, H inverse is equal to H. Okay. Now, see the next property. Now, the converse of this theorem is not true. That is, H inverse is equal to H, but H need not be a subgroup. Now, see here. If you take G is equal to 1 minus 1, with respect to ordinary addition, multiplication, it is a group. What is the composition table? 1 minus 1, 1 minus 1. If you write dot 1 into 1, 1, 1 into minus 1, minus 1, minus 1 into 1, minus 1, and minus 1 into minus 1, 1. This is the composition table. Is it? This is the composition table. If you see all the entries belong to G, all the properties are satisfied. Therefore, this is a group with respect to dot. If you take H is equal to minus 1, it is a complex, but it is not a multiplicative group because minus 1 into minus 1 is plus 1. It is not an element of H. Closure property itself is not satisfied. That means the converse of this theorem is not true. Okay. Now, see the next one. If H is a subgroup of a group G, then prove that HH is equal to H. Now, product of two subgroups itself is a subgroup. Okay. Now, take X belongs to HH in order to prove that. That means X is of the form H1 into H2 by the product of definition of product of complexes. In the first slide we discussed. Now, this is X is equal to H1, H2, where H1 belongs to H, H2 belongs to H. But H1 comma H2 belongs to H, H is a subgroup of G. Therefore, product of those two elements also belongs to H by closure property. Therefore, X belongs to H. Where you have taken X belongs to HH and you got X belongs to H. Therefore, HH is proper subset of H. Similarly, H, take H belongs to H. H belongs to H. H is a subgroup of G. Therefore, H can be written as H into E, where E is the identity of H. Now, here consider H as element of this H and identity as this element of this. Therefore, HE belongs to HH. You have taken H in H and you are able to say that H belongs to in HH. Therefore, H is the proper subset of HH. So, from 1 and 2 you can say that HH is equal to H. Okay. Now, thank you.